Today we will be talking about file formatting and solution evaluation of your approach. As a reminder, all webinars are being recorded. We are recording them. We are then posting them on YouTube. You can already go to YouTube and find the prior two webinars online. If you Google, again, ARPA-E Go competition, you're going to find a selection of different hits. I have provided the links as well, though, but this is, again, the Secretary of Energy advertisement of it. This is our workshop last summer, which is, again, a bit outdated, so there may be some things a little off in that in regards to when we launched it. But this is the webinar 1 that we launched a few weeks ago. Here is webinar 2 that we had just last week, and you can see them again here, okay? And the links are also provided in the slides, as you can see. The third, this one will also be posted very soon. All right? Another reminder, please submit your questions to the host of this webinar. That person this time, is Rob Brown. I gave you a quick print screen snapshot of what you should be finding in WebEx. Find that person, Rob Brown, listed as the host. Send your questions to him. We will compile the questions and address the questions at the end of the webinar. Another reminder, if you did not receive an email from me announcing this webinar, then you are not on my email list or something went wrong. In either situation, if you want to be on the email list, email me, corey.hedman@hq.doe.gov. You want to be on the email list, email me. You want a general inquiry question associated to the Go competition Challenge 1 or future competitions, any other questions, you can email me. You can also email the Go competition administrator, which is Pina Nanel, which is their email is posted on their website. Okay? Moving along, Trial 1. We keep reminding you, we're going to continue to remind you, we want you to prepare for the Trial 1. It is upcoming, April 1st through the 15th is when you can submit. We mentioned this last time, but as a reminder again, you get one submission. So make sure that that's the submission that you want, okay? And also we want to remind you, be active on the leaderboard. More information is on the website. Go to that website. There's a lot of information. If you go to competition and then Challenge 1, you're going to find the problem formulation, input and output file, format requirements, data sets that are already available, the evaluation mechanism, the scoring mechanism, and the leaderboard itself. Okay, so once people start using more actively the leaderboard as opposed to the sandbox, you'll start seeing people's scores showing up at the leaderboard. Okay? Another quick reminder, the data sets that have been released thus far are the ones that will not be used in Trial 1, but you can play with them and you can use them to show how you are doing in the leaderboard. But after Trial 1, whatever we use in Trial 1 will be posted ex post so that you can test them, test the data sets and your approach more closely, see where you're going right and where you're going wrong. Okay? And of course, we'll lead up to, with that, to Trial 2 and the same thing. All right, so there have been some questions coming in and some misunderstandings as to the intent behind Code 1 and Code 2. We spoke about that last time in Webinar 2. We're going to speak more about that today in this webinar in regards to file formatting. I want to provide everybody a more thorough description as to the intent of, and the design of Code 1, Code 2, Solution 1 text file, Solution 2 text file, and the time limits associated to Code 1 and Code 2. And with that, the time limit associated to your generation of your output file, Solution 1 or Solution 2. Okay? The problem that we are providing to you is known as a two-stage stochastic program. Okay? There is the first stage from Power Systems perspective, that's our base case, and the second stage, which is the post-contingency case. The right way to solve this problem is to solve the entire problem altogether, considering all contingencies, to make sure that you get a common base case solution that's reliable against all single contingencies that we are defining for this security constraint optimal power flow. Okay? That's That's the best way of attacking it, is to solve it all together. Okay. However, there is a problem associated to the size of the problem. It grows in size as we add contingencies, and it's non-convex, as I'm pretty sure everybody on the phone knows. It's not an easy problem to solve. The intent behind giving you a code 1 and a code 2 is that there are contingencies that very well are easy to handle. Okay? In existing practice in industry, contingency screening occurs. Before you solve a security constraint unit commitment at the day-ahead time stage, or a security constraint OPF, or a security constraint economic dispatch, there is a down select of what constraints and variables to model. There is a down select as to what contingencies to model. That's what goes into the optimization engine. Okay? Now, as we advance technology, we want to be able to handle more and more complexity to do a better job with the optimization. However, the intent, again, behind Code 1 and Code 2 is to acknowledge that teams may be able to predict that certain contingencies may not need to be tracked when they're generating their base case solution. We are not suggesting that you only solve the base case solution in Code 1. Code 1, as shown in this picture, is likely to be a combination of your base case and some subset of contingencies from the entire contingency list. So you then solve in Code 1 whatever you choose to solve out of the contingencies, and you produce from that two-stage problem in Code 1 a first-stage only solution. Then the first-stage solution that you produce is passed into your Code 2, and the contingency list, the full contingency list, is then solved in your Code 2. So if I have a PGM-sized system of 15,000 buses, and 10,000 contingencies, and I think that 5,000 of the contingencies are critical, I will be okay to ignore the other 5,000. My Code 1 would have those 5,000 inside it. My Code 2 will have all 10,000 inside of it. My Code 1 will produce the base case solution that is guaranteed to be secure across those 5,000 that I selected. Then I have to pass it to Code 2. Code 2 will then solve for the remaining 10,000, for all 10,000, and if I guessed wrong, I will pay a penalty. And if I guess right, then good on my behalf. Okay? So the structure of the Code 1 and the Code 2 is to encourage people to consider contingency screening procedures, basically at the initial stage of your approach, because that's exactly what will happen in reality. Is that the user is going to come to your tool, and even if they give you a large selection, your approach is likely to do a down select, solve it, and then come back to the full listing of contingencies. So again, I just want to reiterate, it is not as if we expect you to solve only Code 1 in base case and then solve only the contingencies in Code 2. That is likely to produce a very bad solution, and we do not want that. I would encourage you, if you are confused based upon what I just described, I try to give a lot of details, but if you're confused, put them into the questions. Again, Rob Brown, okay? Put them into the questions associated to the webinar. That's item 1. If you want to take it more offline, there's my email address. Email me, okay? All right, with that, I'm done with my introduction. I'm going to be handing it over to PNNL. Again, in general, if you have any questions outside this webinar, questions for the webinar, go to Rob Brown. Questions for the general competition, go to ARPA-comp@pnnl.gov, which is the Go competition administrator for us, PNNL, or to me. Okay? Thank you. With that, I'm going to pass it over to PNNL.
So I'm going to talk about file formatting and solution evaluation. I'll begin with the format of the input data. So a single instance of the competition problem consists of 4 files. These are referred to by their file suffixes: a raw file, an ROP file, an INL file, and a CON file. The raw file contains the basic information about a given power system. This is buses, loads, fixed shunts, generators, lines, transformers, switched shunts, and areas. To avoid any confusion about this term switched shunt, that's just the name of the section. We are modeling our switched shunts as continuous shunts. So often you'll see the terminology controllable shunt, or CS to abbreviate that. The ROP file contains parameters for defining the cost functions of generators. These are sample points on piecewise linear cost functions. The INL file gives you the participation factor for each generator. The con file gives you a list of contingencies. Each contingency is either a generator outage, a line outage, or a transformer outage. So each contingency listed in the con file specifies exactly what piece of equipment is going out. These data files are valid instances of a common industry format. This is the PSSE 33.5 format. By choosing this format, we're not saying that you need to use PSSE software or that you even should use PSSE software. That we just wanted an existing format so that just for convenience, really. A complete specification of the fields in these files that we're using and just how they're formatted can be found in Appendix A of our formulation document. The formulation document contains many appendices, and I'll be referring to them at various points in this presentation. At the end, I've got a table of contents printed out so that we can refer to that easily. There is a Python code that we've written to read input files. This is available at a public GitHub repo. This repo contains lots of stuff, so I'll go through that later. The output data, this is the solution that your code needs to produce, consists of two files, a solution1 file and a solution2 file. The solution1 file contains your base case solution. This is the operating point consisting of bus voltages and generator outputs. And then a solution2 file, and that's the solution that occurs after each contingency. These will be created by code 1 and code 2, respectively. And the solution1 file will be read by our evaluation platform after your code 1 completes, but before code 2 runs. You won't be able to change solution 1 during your code 2. Then your solution 2 file will be read after code 2. For a little more detail on solution 1, it consists of two sections. There's a bus section and a generator section. In the bus section, for each bus, you list the bus number, the voltage magnitude, the voltage angle, and the total susceptance of controllable shunts at that bus. That could be 0 if there are no controllable shunts at that bus. The generator section consists of a single record for each generator containing the bus number of that generator and the generator ID, and then the real power output and the reactive power output of that generator in the base case. Then in solution 2, for each contingency K, we have a similar structure with a bus section and a generator section. But in addition, you need to provide the contingency label for that contingency. And then there's one extra variable in a contingency, and that's the delta K. So that's a scalar for each contingency. You can find a specification of the output file formatting in Appendix E. This is section 2 of Appendix E. And there is code for reading the output files, and that's again in the evaluation repo, along with other things. The solution files are reported in the same unit convention as the data files. We've called this the data unit convention, as opposed to the model unit convention. These units are per unit for voltage magnitude, degrees for voltage angle, and megawatts, MVAR, etc., for real and reactive power. This unit convention is described also in the problem formulation document. Here's an example of a valid solution file. And then so this is solution 1. After that, I'll show you solution 2. So again, there are two sections, a bus section and a generator section. Each section has a header row describing the fields. And then after the header row, there is a record for each bus in the bus section, a record for each generator in the generator section. And it's just exactly the data that you need. So it's the bus number, voltage magnitude, voltage angle, and total susceptance of controllable shunts. And in a generator section, it's a bus number, a generator ID, which is a string, one or two character string, the real power output and the reactive power output. And in solution 2, here's an example with two contingencies. So this is read, we've printed out two columns, but this would be a single file, and it reads starting from this line, the first contingency, then after that is the next contingency. So the first contingency is identified by a label, that's a string. Then there's the bus section, similar to the base case bus section, the generator section, similar to the base case generator section, and lastly there's this delta section, which is a scalar for each contingency. So in this contingency we've got 50 megawatts is our delta, and in the next contingency we've got minus 30. Just one note I'd like to put here, the delta values are not necessarily equal to the total generation that is lost in a contingency. For one thing, the participation factors don't necessarily add up to 1. That said, there are units on the delta value. The units are megawatts, and the units of the participation factors are dimensionless. Here is an example of how our evaluation platform will run your code. So this is an example showing how we run it for a single scenario. That's one instance of the problem. This is an example using Python. So you would provide two code files, myPython1 and myPython2. This is synonymous with the more general code1 and code2. First, our platform runs myPython1, and we've got a number of arguments. So there are 4 input files. There's a time limit, a scoring method, and a network model, and then the output is printed to myPython1.log. The 4 input files, again, are the PSSE formatted files. They are listed in alphabetical order here, the con file, then INL, then raw, then ROP. The next argument is a time limit. So this is the time limit for your myPython1. It's 600 seconds for divisions 1 and 3. That's the real time, and 2,700 seconds for divisions 2 and 4. It's the offline. The next input argument is the scoring method. That's just an indicator telling your algorithm how the results will be scored. There are 2 scoring methods. There's the objective function scoring. So your score on a particular scenario, your score on a data set is the geometric mean of your objective functions across that data set. And the scoring method 1 is this performance profile method. The network model is a string that identifies the network model of the input files. So a number of scenarios will be constructed from basically a single network. And we believe that some entrants may want to take advantage of that knowledge. So your MyPython1 code needs to write solution1.txt. Our platform reads that solution1 file, and then our platform runs your MyPython2 code. Now, there are similar arguments in MyPython2, the same input files, the time limit, the scoring method, and the network model, and it prints output to mypython2.log. The main difference here is that the time limit is generally much larger, and we want to give you as much time as you need to actually write the full solution for each contingency, but we have to put some limit in order to stop codes that are just hanging, essentially. MyPython2 potentially reads solution1.txt so that it has access to what you've already determined your base case is. What it needs to do is to write solution2.txt. Then after MyPython2 completes, we will read your solution2. You should write your output in the same directory that your Python code sits in. I want to emphasize again, you cannot make changes to your solution1 file after MyPython1 runs. I should say you can rewrite your solution1 file, but we won't see it. We're going to read it right after MyPython1 runs, and anything after that we won't see. Again, time 2 is much longer, so that you can compute and write the full solution of each contingency. And again, this is arranged this way because we want to reward algorithms that are able to quickly solve the base case by avoiding solving each contingency. But at the end, we do need the contingency solutions in order to do the evaluation of your solution. I want to take a pause if there are any questions at this point. Okay.
Yeah, so we're compiling, a lot of people are muted, so we're compiling questions here at ARPA-E and working them into slides, and we'll address those at the end.
Okay. Next, I'd like to go over the solution evaluation process. So first of all, what we mean by the word evaluation is we read your solution1 and solution2 files for a single scenario or a problem instance. Then we determine whether whether the solution that you wrote is feasible, and we compute its objective value. Scoring is different. This means we evaluate the solution of all scenarios in a given data set, and we return a score based on either of two methods, either the geometric mean of the objective values across all scenarios, or a performance profile calculation. You can get more information on these scoring methods here on the competition website. And the evaluation code, again, is available in this public GitHub repo. So you can run the evaluation code on your own computer, on your own solutions. We definitely advise doing that. The repo here contains examples and syntax on how you would run the evaluation code. If you've got ideas on how to improve the evaluation code or things that you think it really needs, that's fine. You can do that through a pull request if you want, or through emails to us. We cannot pull your code though, so a pull request is okay, but we can't actually pull it. We may review what you've written and incorporate your ideas. In any case, though, we will be rewriting any code that you would submit. So there can be no idea that anybody would be injecting their own code into the evaluation process. And here's how solution evaluation works. So again, we read your solution files. We convert the units from the data convention, that's mostly megawatts, et cetera, to the model convention, which is mostly per unit. We check the bounds on some of your variables. These are hard constraints. We compute the flows on branches and lines and transformers. So the flows are explicit functions of the bus voltage, magnitudes, and angles. So we can just evaluate those functions. Then we compute flow bound violations. These are soft constraints. So we've computed the real and reactive power flowing into a line, for example, at say the origin bus. If that exceeds the line limit in the data, then we evaluate that violation. Similarly, we compute the real power output of each generator in each contingency. So your solution 2 file does provide PGK, the real power output of generator G in contingency K, but we do not use that value. We use equations 84 and 86 from the formulation. This is equation 86. This is actually how we compute the real power output of generator G in contingency K. So you give us the base case real power output, PG, and the delta K for contingency K. We've got from the data the participation factor alpha G and P min and P max for generator G. And we apply this formula to compute PGK. I would say that this computation is analogous to computation of the real and reactive power flows into lines and transformers. So your solution may have a different value for PGK, but we compute it based on what you've provided for delta K and PG. At that point, we've got all of the real power injections and reactive power injections into every bus. So we can then evaluate the real power and reactive power balance at each bus. There will be some violation at each bus, and so those violations are treated as soft constraints. We apply penalties to them. We check hard constraints on generator reactive power contingency response. This is PV-PQ switching. So any violation of this constitutes an infeasibility. And finally, we evaluate the objective, and this is the sum of generator costs and all of the penalties on soft constraints. At that point, we generate the outputs, which is feasibility, is your solution feasible or not, the objective value, and then there's a detailed output file listing for each contingency and for the base case, and for each type of violation, so for each type of constraint, what is the maximum violation and what exact constraint did that maximum occur on? So which bus or which line, etc. That is most of my presentation. I just want to go over that most of what you would need to, most of the details that you might need to look up can be found in the formulation document. So for convenience, I've put up the table of contents here. So this is the main formulation, actually the mathematical model that we're asking you to solve. And then there are a bunch of appendices, including, so Appendix A is documentation of the input data formats. These are the PSSE files. And further appendices telling you how to take those how to take the data that you've read from the input files and transform it into the parameters required by the mathematical formulation of the problem. Then how you would format your solution and how the solution evaluation works. Just for completeness, here's the terminology that I used in this. And at this point, I'll turn it over to questions.
What happens if I submit my code with incorrect formatting? Can I resubmit? So this is in reference to trial 1. No. Be sure to submit using the original data set to work out formatting issues ahead of time. So the reason that these data sets right now are released, the reason we want you to play with the leaderboard, we want you to get to learn the system now before trial 1. Do that, get all the bugs worked out, but you get one submission with trial 1. If you think something went wrong, you can always contact us, but you know, there's no guarantee that there's going to be an opportunity to make any corrections. So get your submission for trial 1, that one critical submission, correct. Can you clarify how the Go competition formatting relates to PSSE formatting? So the formatting requirement that we are using associated to the files is similar to PSSE, but not inherently a specific PSSE version. We've done some minor modifications. I think Jesse would be probably better to explain that. And I would also say from a perspective of ARPA-E that this is not an endorsement for PSSE or Siemens. It's just that we had the choice of how to format the data, and we chose something that's commonly used. Jesse?
Yep. Just our formats are a narrowing of the PSSE formats. So any files that we are releasing as data sets should be readable with PSSE. They are valid examples of PSSE files. However, the PSSE data format is quite flexible, so there are examples of valid PSSE files that are not valid for our competition.
Thank you, Jesse. Next question. Can my code 2 make changes to solution 1? Absolutely not. Okay? So as Jesse went through the sequencing of what happens with your code 1 and your code 2, we will execute your code 1. It'll produce a solution 1 file. We will then read your solution 1 file, create a backup copy on our own end of your solution 1 file, and then we will execute your code 2, which will build upon your solution 1 file to create your post-contingency solutions. Again, I would reiterate my longer explanation from before. Code 1 can in itself find solutions to the entire problem or whatever part of the problem that you want. It is your choice as to what piece of the problem you want to model in code 1, but we are only taking from whatever you put into code 1 what is required for solution 1, right? Okay? But you cannot modify solution 1 through your code 2. Why are there time limits on code 1 and not on code 2? Okay, so the general answer that comes back to, again, I would say in terms of how I would see an actual implementation of a security-constrained optimal power flow in reality. Time limits are very sensitive for these problems, right? So if I need to get a solution in real time, and I have a very large system, and my security-constrained OPF solution can handle 90% of the contingencies that I want it to handle, I'd rather get that solution out of it than have no solution to work with for my system, and then let it keep churning over the extended time for the remaining. Basically, that's the intent of code 2 having not having a solution time limit. From a technical algorithmic perspective, right, the as we progress in algorithmic advancement, if you can handle 100% of the entire problem in code 1, that will guarantee, that gives you the opportunity to get a better solution. I would suggest that. I would suggest you handle as much as you can in code 1. But code 2 is there to just basically do the post-processing of these contingencies that you anticipated to not be active, to not influence your system. But you need to ensure it, right? So if I have a 500 kV line that's at 20% of its capacity, or 5% of its capacity, some extreme example, right? How critical do I think that contingency is going to be? Or if I have two generators at the same bus, one is very large and one is very small, n-1 dictates that I have to be able to survive the loss of the large one. Okay, so how significant is it going to be the case that the second one, this very, very, very small one, will be an influencing factor to my base case? There are situations that you should be logically able to filter out such that they're less critical, and that is your choice. That's why we're allowing the code 2 time to have this longer time process behind it. We are also, of course, doing it because the handling of all the contingencies and the production of solution 2 file. The solution 2 files themselves are not small, and so we're trying to remove the efficiency of Team 1's approach in terms of simply writing a file versus Team 2's approach of writing an output file of a massive size out of the evaluation procedure. Okay, so that's why solution 2 is set aside to have a different solution time. It's not done for you should only solve base case in code 1 as I described before and only contingencies in code 2. Okay. All right, does solution 2 contain solutions for contingencies? Yes. Okay. So your solution 2 should be producing your contingency solutions, right? Code 1 can be whatever you want it to be in terms of what you solve. Code 2 should be handling the post-contingency states. Solution 1 and solution 2 must follow our requirements. All right? Can you use my PGK for the contingencies? No. As of right now, what we are doing is we're taking this projection formula as shown here. We will be calculating PGK relative to your base case PG outcome and this participation factor times by this floating free variable delta K to produce your PGK. And then if, PG plus alpha G delta K exceeds one of the bounds, you get the bound. And if it doesn't, then that means that you're following exactly your participation factor and PGK should equal it. Okay? Again, this is a representation of the complementarity conditions inside of the software, in the formulation. We anticipate all generators to follow their participation factors for the contingencies that they're supposed to respond accordingly to, as long as they don't reach a bound. So I follow my participation factor until I reach Pmin or Pmax, and then at that point I just sit at Pmin or Pmax, and whatever I was expected to produce that I cannot produce, essentially through the formulation we've structured, gets built into other generators and their participation factor, right? So think of it this way. There are two generators that are supposed to inject 10 megawatts, each of which is supposed to provide 5 megawatts. If I can only provide 4, naturally the formulation will address will be adjusted to make sure that the other guy is providing the 6, okay? And then we impose in our evaluation, again, this projection formula. I found an issue with the evaluation code and have proposed a solution. Can you commit my changes to the code on GitHub? We will not commit any competitors' changes to the evaluation code directly. If you believe there is a problem, you contact us. We will evaluate what you suggest, and then we'll make changes to the evaluation code as necessary. We do very well appreciate and welcome and want feedback. If something is caught to be off, let's take care of it sooner rather than later. Notify us. We will investigate and we will respond. I have submitted an approach. Why can't I see my score on the leaderboard? So first, you need to submit to the sandbox. If you submit to the sandbox, and once you get qualified for the leaderboard by showing successful submission with the sandbox, you can post to the leaderboard. But posting to the sandbox does not post to the leaderboard. That's one clarification. Okay? And then it comes down to whether you have a valid approach. If your valid approach is not producing appropriate output files relative to our requirements and it's failing, then you're not going to be posted on the leaderboard. There was an error a few weeks ago associated with somebody's submission to the leaderboard, and that error was on our side, not the submitter, but we have taken care of that. So the leaderboard, as far as I last heard from P&L, is ready to go. And so when you submit to the leaderboard, if you have a successful submission, again, after passing the sandbox stage, it should be showing on the leaderboard. I want to see the leaderboard start populating. So I want that to happen. We need that to happen, so let's start getting that to happen. And then the other comment here is just a reminder, it's good if you can, well, not good. You should be testing the original data sets before trial 1. Okay? All right. Next question. Is there any chance that there might be an islanding after the contingency takes place? So the way that we're structuring the selection of the contingencies and the way that we are preparing the data, the answer is no. Now, this can happen in reality for a variety of different reasons. Topology processing may have basically a floating bus somewhere out there that really is not impactful for the power flow, and if you simulate the contingency and the contingency list wasn't updated, maybe it causes islanding. Or maybe your system splits after it has had multiple events already occur and a next contingency does that. But basically for the competition, our focus on N-1 is under the assumption that a single contingency does not split your system, because that's generally the main design and approach from planning to operations for our larger interconnected systems. Other places throughout the world may be less interconnected, but relative to what we're assuming targeting for the North American reliability requirements, there should not be an islanding result as due to a single contingency event, and we do not have that in our data set. Will there be transformer contingencies? Absolutely. N-1 applies to transformer, N-1 applies to generator contingencies, we have them, and transmission contingencies. In reality, an ISO or a utility will model more contingencies, frankly, than what we have in our competition. What we have in our competition is basically generator contingencies, transformer contingencies, and transmission line contingencies. Okay? We have a bus branch data set structure to all of our data sets. We do not get into a node breaker model or a bus breaker model. Actually, that type of information will come, situations will come in challenge 2, not in challenge 1. And so with our bus branch configuration, you either lose a transmission line or you lose a transformer. We are not simulating the loss of, the operation of a breaker on one side of a transformer or a transmission line and not the other. It is both breakers operate on both ends of the line or transformer. That's the type of a contingency that you're going to find. And that happens for the transmission, higher voltage, not subtransmission network. Should we treat each contingency differently and find the solution of the OPF individually, or should we consider them happening altogether and we are supposed to find the solution of the OPF problem altogether? So how you want to solve it is completely up to you. I have my suggestion, though. N-1 dictates that I must find a first stage solution, a base case solution, that single base case solution can then deviate relative to the rules that govern the movement between base case to post-contingency, can deviate to the post-contingency state and achieve feasibility. That base case solution should then be a solution that is constant across all contingencies. You solve contingencies independently, you get different base case solutions potentially. That's not valid relative to the formulation that we posted. It's also not valid based upon N-1 standards. So if you were to produce a solution of that form, you could very well get a very bad score. However you want to try to approach this problem is up to you, though. You could use a decomposition subroutine that takes into account that type of an attack from an algorithm perspective and then tries to pull the base case, independent base cases together. That's an approach. The approach is up to you, but you must conform again to the formulation that we have specified. if we compute optimal participation factors at the base case solution, and if our optimal participation factors vary substantially from the ones provided, what should we do? Well, the quick answer on that is you should again refer back to the formulation. So our formulation has provided participation factors to you. So if you do not follow the participation factors or the complementarity conditions associated to, as I was describing earlier, when I reach my bound, I can no longer follow that participation factor, then you will be in violation of the formulation. And if you're in violation of the formulation, there will be most likely a large penalty associated to your inaccurate solution. Okay, so challenge 1 is taking the approach of imposing a general practice in industry, which is our assumption is that generators will naturally follow a participation factor. So there are requirements associated to the post-contingency answers, or again, second stage answers, based upon these predefined, predetermined, offline-driven participation factors. This is a key feature of Challenge 1. It will be imposed in Challenge 1, and guess what? In Challenge 2, you're going to find something else, because then we're going to see, okay, what methods do well under this assumption, this operational assumption? What if we want to determine optimal participation factors in the future and deploy that in industry operations? Who would then win? So this is something that you're going to see being addressed in Challenge 2. It is not being addressed in Challenge 1 because we are following that industry standard as of now. How can I stay informed of any evaluation changes? We do not anticipate changes. We are in the mode of trying to minimize the amount of changes that we will introduce. Of course, we understand the critical nature of that associated to a competition and the strategies you may or may not take as things may change. Of course, it is in our own interest to make it be as limited in terms of disruption to you as possible. We do not want that. But to stay informed, you should be checking the website. You should get on the email list. You should be contacting us if you think something's off. Will there be any more webinars? We do not have any additional webinars planned at this time, but there most likely would be something probably in the future. Could very well find a webinar, especially after Trial 1, if there are other, say, confusions or other things to clarify. We may have a webinar focused on, say, understanding the formulation or understanding the scoring, just as I discussed today, understanding the purpose and intent of Code 1 and Code 2, in terms of how that may affect your algorithmic approach. So at this point in time, we have nothing scheduled as of right now, but if we decide to go that path, we will notify you again through the ARPA-E website, the PNNL website, and my email list, okay? I would also say with that if you have suggestions or requests associated to additional webinars, if these have been very helpful and you would like to have more on particular topics, feel free to make suggestions. Okay, so that is one listing of questions that I have. I have more that are coming to me via email from my team. So bear with me now as I read the others, okay? I'm just going to put this back up here. All right. Is there any chance that there might be islanding after the contingency takes place for the data set? So I already addressed that. Sorry. The answer is no. A good competition. Okay. 1 second. I guess I have a repeat of some of these questions. Let me filter them. So there's a question, is it correct that the solution 2 file is per contingency? The solution 2 file, there's one file for one data set scenario, and that solution 2 file contains all of the answers for all the contingencies for that one data set, for that one scenario of that network model. Sorry. Okay. All right. Let me
Corey, there were 2 additional questions, and I believe Ashley just sent out slides to you addressing them.
Okay.
If you want to use those.
I will pivot to those in a second. So let's see. All right. Doesn't the code 2 and therefore solution 2 depend on the base case solution, solution 1? Absolutely. Okay? All right. The question is again, doesn't the code 2 and therefore solution 2 depend on the base case solution 1? Question is yes, absolutely. Again, I'll give an example. I'm very confident that out of the 10,000 contingencies that I have, I only have to model 4,000 of them. I will put into the code 1 a mathematical program that is a two-stage problem that has 4,000 contingencies represented for the second stage cases. I will solve that. Maybe if I have more time, I'll try to go back and add more contingencies to that code 1. But I will go through and I'll solve after I've done some sort of down select, and I'll generate then a first stage solution and a second stage solution for the contingencies that I was modeling in code 1, those 4,000. Okay? But the output of code 1 is only solution 1. So then I take the first stage base case answers and I spit out, given the requirements, I spit out the base case solution that I get from my two-stage stochastic program in code 1 relative to the 4,000 that I was modeling. Then I take that base case solution, my code 2 code will call upon the solution 1 output file. It will pull that into the code 2. I will have to enforce inside of my code 2 that I must respect and not change, deviate away from, the base case first stage solution that comes from solution 1 relative to the requirements of the formulation. So when the code 1 says that generator 5 should operate at 500 megawatts in the base case, code 2 is going to have generator 5 at that 500 megawatts or whatever it was I said, 500 megawatts for its base case, okay? And then given the 500 megawatt decision from code 1 and reported in solution 1 file, right, for generator X outage, it will have to follow its participation factor. And so therefore the solution 2 file for that contingency is going to take that generator 5 from 500 megawatts and move it relative to the participation factor. Then that'll define the injection of that generator for that particular generator X contingency. You then will also, through that solution 2 file, generate a power flow result for each of the contingencies that you're required to solve. Okay? So, absolutely, code 2 and solution 2 do depend on the solution 1 output file. Absolutely it does. All right? So I'm looking, Ashley and Dave, at the second slide you sent to me, and there seems to be something formatted wrong for me to view it right now. So I can't really read it. So let's see. Some more questions. I'll come back to that one. If you can resend the second one to me, I'll mark it.
So Corey, I can just read.
Go ahead and read it.
The answer. So the question is, what happens if in solution 2 there's a wrong value of delta K in the contingencies? The answer is that delta K is a value that you choose and solve for as part of your submission.
Right. So Dave is right in his answer. This delta K is kind of like a floating variable. So everybody can think of it this way. If I lose forget about losses in an AC network for simplicity, though you do have losses, but forget about losses. If I lose a 1,000 megawatt generator and every generator that is anticipated to respond to that contingency, their participation factors add up to 1, then basically my delta K is 1,000. But again, based upon this complementarity condition where, all right, I expect the generator to produce 20 megawatts in response of that contingency, but it reaches its limit before it produces 20 megawatts. That delta K there is there to float to basically adjust its value relative to the residual generators remaining that provide response while following the participation factors. okay? Let me explain it in a different manner. So let's go back to my 1,000 megawatt case. So the 1,000 megawatt case, that's what I'm expecting to be across the system. There's subset A of generators that respond but reach limits. Then there's subset B of generators that respond and follow their participation factor perfectly, okay? Whatever is the amount of megawatts that the subset B needs to provide, delta K should adjust accordingly such that whatever the sum of the participation factors are with the generation in set B, that delta K corresponds to the needed impact associated to what they need to provide. Okay, so the formulation naturally allows for the ability to adjust to this fact that you expect all generators to follow their participation factor, but some do not. And then for the ones that do, there needs to be some sort of an adjustment because their participation factors don't add up to 1. Okay, and that's the delta K. All right, next question. Let me see. So I handled the other ones in that email. Let me see this next one. All right, sorry. Okay, here's another question. If I understand correctly, the input of code 2 doesn't include solution 1 according to reference to the website. This doesn't make sense because the solution of code 2 should depend on the base case. Okay, so that's a question that comes back to what we talked about before. So code 2 should rely upon solution 1. So if there is something on the website saying that that is not the case, then that's not correct, and we will look into that and correct it. But code 2 does depend on your base case solution, and your base case solution is reported in solution 1, okay? So I think that's clear. It should be clear now.
Corey, this is Jesse. There was a further email from the participant about this. And I think the confusion is, will they have access to the file name? And our answer to that is basically you can hard code solution1.txt in your code 2. That will be the file name, and it will be in the same directory that you wrote it in. It will be in the directory that your code is running in. It'll be in the directory that contains your code.
Okay.
So we don't need to provide it as an argument.
That is an important point, so everybody should take note exactly of what Jesse just said. Okay. So you will need to be able to call in the same directory your solution 1 output file in your code 2. Okay? All right. Next question, going through them. Why does the input to my MATLAB 2 not have solution1.txt? My MATLAB 2 needs solution1.txt to generate solution 2. So,
Jesse just answered that question. Basically, solution 1 is not a variable. The other input parameters are variables. Hard code solution1.txt into your MATLAB 2, as Jesse said.
Okay. Sorry for a bit of repetition there. So, okay. So I don't see any other questions. So if Dave or Ashley, if I'm missing something, please let me know or read it yourself.
So as we were talking, we just got 2 sort of last-minute questions. So I'll put you guys on the spot right now. So the first question is, can code 2 consist of code 1 plus the additional code to solve the contingency? And question 2 is, what is the difference between hard and soft constraints?
Okay, so first question, can code 2 contain pieces of code 1? Okay, the short answer on that is you can put whatever you want into code 2 as long as you're following the rules. So what are the rules? Your code 1 can, again, contain whatever you want it to do. It needs to then export the solution, the 1 file, which requests, as I think we went over in webinar 2, the base case solution. You know, What is my base case set point for this generator? What are my voltages? All of this information for the base case needs to come out of code 1. You can solve much more in code 1. I would advise you to do so, but what is required as the output of code 1 is a subset of what you're solving in code 1. Then you take the code 1 output, which is that solution 1 text file, and your code 2, as we've been discussing, needs to read it. It reads it. It needs to follow through with solution 1 answers, okay? So if you have, again, a generator at 50 megawatt set point in base case for your solution 1, and your code 2 changes it to be 60 megawatts, you will be producing a solution 2 output file that's inconsistent with your solution 1, and you will be penalized because they will not properly align, okay? So all of this is dictated based upon basically, A, the formulation, which, as I know, a long document, but the formulation online. So the formulation online gives you the entire description of the full extensive forms, security-constrained optimal power flow. That is what you're going to be judged by. It is up to you how you want to parse it between code 1 and code 2, but it is not up to you in terms of following our output requirements of solution 1 and solution 2. You follow our output requirements of what to provide to us in solution 1. Whatever you provide in solution 1 must be, you must abide by that for your base case when you determine your solution 2 file, and then you must have solution 2 file abiding by our rules associated to what that format should be. And then, of course, tying it back to the formulation. How you want to handle code 1 and code 2 is all up to you in terms of what you think should be solved where, but you have to follow the formulation, you have to follow the outputs, and the specifics as to how you are penalized when you deviate away from those requirements is in the scoring guide. The other question was what, Dave?
The distinction between hard and soft constraints.
Okay. Different people mean different things when they say a hard constraint or a soft constraint, but basically what you should take away as those soft constraints, those are the ones we have basically relaxed. We have put slack variables on some of the constraints. Again, refer back to the formulation. And with those slack variables, they show up in the objective function. You will see that in the formulation, and they have penalties associated to them. So by soft constraints, we are basically saying, even though the true line limit of this transmission line is 500 megawatts or 500 MVA, if you end up violating it with your power flow solution and you get 510, you're going to get a penalty on that 10 megawatts or 10 MVA, okay? That's basically then a soft constraint. We are allowing you to violate it from the true limit, okay? But then the violation just gets penalized. That's an addition of a slack variable into the constraint and the addition into the slack variable into the objective. And then the hard constraints is basically everything else where we're basically forcing you to abide by them fully. Other questions?
It looks like we have one final question. In reality, what is the variable subsistence of a bus?
I'm not following the question. Say it again.
In reality, what is the variable subsistence with a bus?
So what I believe the question is meant to ask, what is the susceptance value of a bus? Okay, so if that's the question, all right, so that's basically a node in this network flow model. If that's the question, the value of the impedance of the bus is basically to the point of when you are solving these security-constrained OPF problems, it's basically next to negligible, so that you have impedance values for transmission lines and transformers and other assets, but the bus itself does not have a representative impedance value.
This is Jesse. I think that question is referring to the final column in the bus section of Solution 1 and Solution 2. And that column is BCS, right? That is the controllable shunt susceptance of bus at a given bus. So
that makes more sense. Then I think Jesse is answering the question.
Yeah, if I may. So some buses have switched shunts. They may have one or more than one. some buses have none. What the solution format is asking you to do is determine the total susceptance of switched shunts at each bus. And that's a variable in your model, right? So you choose that value within bounds, and it's asking you to write that value in. That's it.
Anything else, David?
Nope, I think we're all set here.
All right, well, with that, thank you, everybody. Best of luck. Again, I want to encourage you to be proactive. Don't wait around. If you haven't registered for the competition, do so. If you've registered but not played with the sandbox, do so. Likewise, if you haven't gotten your scores loaded to the leader box, do so. It's very important that we be, as a group, proactive to make this a successful competition. We look forward to interacting with everybody as we go forward. Again, if we have any other webinars, we will let you know. If you have any suggestions for us, please let us know. Thank you very much. Take care.